Everyone, in this chapter we are going over motion in 2 and 3 dimensions. In the last unit we worried about things going right or left, up or down. Now we can do everything, kind of like these boats. These boats are moving forward, they're moving to the right, they're moving up and down with the waves. There's lots of motions that we can move in real life. We don't just stay in a one-dimensional world. We live in a three-dimensional world where we can be moving in many, many directions. What we need to do is discuss a vector that points from the origin to any location in space. You can see that the particle is located at x, y position. A position vector is written as vector r and points from the origin to that location in space. Since that vector r is in two planes, it has an x component in the I direction and has a y component in the j direction. A way to just write vector r is x in the I direction and y in the j direction. And that's it. You don't have to do anything. You know how far east and how far north you'd have to go. If you want the magnitude of that vector, then yes, you've got to use Pythagorean theorem, do x squared, y squared, square root, use some trig to get your angle to figure out exactly where that vector is pointing. But giving it in the IJK format is one of the easiest things to do. And if an object travels from point 1 all the way over to point 2 there, well, that's a displacement. Changing an object's position from start to finish is just the displacement. So you can take vector 1, which starts at the origin, to point 1, and vector 2, which starts at the origin and points to location 2, the difference from final to initial is the displacement. So that's taking r at position 2 and subtracting it from r at position 1. And the nice thing is if you keep it in IJK format, all you have to do in the x direction is subtract the i's. So take x2 minus x1, that'll tell you how far right or left you went, and do the same thing with y2 minus y1 in the j direction. That'll tell you how much up and down in the j direction you went. To find the magnitude again, you have a complete I component and then a complete j component. Pythagorean theorem and trig will get you your answer. Showing you what we can do and how we can write out the displacement. Position vector has an I and j component like we discussed, and the change in r is r2 minus r1. So what that means, it's really x2 in the I direction plus y2 in the j direction minus x1 in the I direction and y1 in the j direction. So having those two pieces of information, what we can do is actually combine the i's together and combine the j's together. And what you'll be left with is x2 minus x1 all in the I direction. We're going to add that to y2 minus y1 in the j direction. And that's how you get your two pieces for your x component, or for your r vector. To find velocity, well, we know velocity is just the change in displacement over time. And since our displacement now has two pieces, what we're going to do is take the derivative of those two pieces. So I'll do dr over dt. So that means I must take the derivative of x with respect to time for the I direction. I'm going to add that to the derivative of y with respect to time in the j direction. What that will give me is a velocity in the x direction and a velocity in the y direction. That will give me my complete velocity vector in 2 dimensions. So there's a vx and a vy component. If I wanted to find the magnitude, I could just simply take the square of both values and square root, just like we did with Pythagorean theorem. And if I wanted to find an angle, say I have the x component to the right, that's vx, and I have the y component up, that's vy. That means the true velocity vector is right here, at this angle. And if I wanted to solve using the angle, I would just use some trig. Looks like opposite and adjacent will give us the angle using tangent. since we know the definition of acceleration, acceleration is a change in velocity with respect to time. If I want to find something's instantaneous acceleration in 2 dimensions, I just take the derivative of my velocity vector with respect to time. That means I've got to take dv in the x direction with respect to time and add that to the derivative of the y component of velocity with respect to time in the j direction. That'll end up giving me my full acceleration value. But remember that velocity is the second derivative of position. So really, if you know your position equation off the bat, you could do the second derivative of position with respect to time in the j direction and add that to the second derivative of y with respect to time in the j direction. That will also give you your acceleration. Just like we just saw with the velocity, if the acceleration has an I and j component, you can combine them to give you the magnitude of acceleration, and if they're at an angle, use trig to solve for the angle of the total acceleration. Let's try an example here. We have r, which has a 1.5 plus 12 meters per second t I component, and a 16 meter per second times time minus 4.9 meter per second squared times time squared j value. The first thing I want to do is let's break these into the x and y pieces. Let's know which part we're dealing with. The x direction I will highlight in blue. That's easy. It's everything here attached with the I component. What's the y is everything that's highlighted here in green. That's everything here under the j component. If they asked you for the x and y pieces of our position vector, all you have to do is look for the i's and j's and rewrite them. If I want to find the x and y velocities, well, we know that velocity is the derivative of position with respect to time. To find the x velocity, I take the derivative of x, and to find the y velocity, I'm going to take the derivative of y. The derivative of x here, 1.5 becomes 0, and you're left with just 12 meters per second. There's my I component for velocity. My j component's a little more tricky. It's 16 meters per second, doing the derivative of 16t, and then taking the derivative of 4.9t squared, I get minus 9.8 meters per second times time. And that's the j component. I now have the x and y components of my position vector. I now know the velocities. If I wanted to get the accelerations of each of those, well, the x acceleration is just the second derivative of position, or the derivative of velocity, which in the x direction becomes 0. There's no acceleration in the x direction, and in the y direction, again, second derivative of position, or first derivative of velocity. The 16 goes away and leaves me just a negative 9.8 meters per second squared as my acceleration in the j direction. Just by looking at this problem, whatever that position vector is telling me, I know that the accelerations, there's no acceleration in the x direction, and it's actually in free fall in the y direction. So however this object's moving actually is describing a scenario of something being in free fall. Like we said, the velocity is the change in displacement over time. To find the instantaneous velocity, just take the tangent line of that path, or take the derivative of your position vector with respect to time. Same with acceleration. Acceleration is the change in velocity with respect to time. So to find that instantaneous acceleration of something that is moving in more than one dimension, just take the derivative of velocity with respect to time, or the second derivative of your position vector. Velocity and acceleration vectors can be broken into their components, and when you break them into their pieces, you can recombine just their pieces to get a complete x component, y component, z component, and combine those to find the magnitude and direction of the real velocity. We've shown you in class many times in the last chapter that we can represent motion with dots, just showing where the object is at any moment in time. And what they're trying to show you here is that if you look at v2 and the velocity at time 4, you can subtract those two velocities, final minus initial, and you get that change in velocity there. The change in velocity is proportional to the acceleration of the object. So we'll go through a couple examples where we'll look at motion maps and try to determine where the acceleration is pointing for an object that moves in more than one dimension. Scenario, why don't you imagine a car going up and over a hill, and as it's going up and over the hill, so you can see as the object is coming up and around the bend, our velocity vectors are changing as we go up and around that curve. And if we pick two velocities, these should show us that we have a change in velocity or an acceleration in a particular direction. So if we call this VF and we call this VO, do our vector subtraction, change in velocity is final minus initial. So the minus initial is back in this direction. Here's your final, and here's minus VO. What that gives us is a change in velocity in that direction. So as you're going around that bend, you are actually changing your velocity or accelerating in towards that bend, just taking the final minus the initial vector. We can try that on another scenario where an object may be going in a complete circle. With a complete circle, at one moment in time, the object is heading straight this way. At the next moment in time, the object is heading up. At the next moment, the object is heading to the left, and then the object is heading down. So as you're moving around the circle here, it looks like you're always trying to go straight away from the circle at any point in time, and we can pick any of these to figure out the acceleration. I'll pick this as my VO, and I'll pick this as my VF. In your notes, why don't you try picking two other places and seeing if you get a similar acceleration. If I do VF minus VO, that's taking VO and flipping it, pointing in that direction, my change in velocity is inward. So as I round the bend here, just using a motion map, I can see that I am accelerating in towards the center of that circle there. We'll talk more about this later in the chapter and in future chapters.